Hello everyone, I'm Joe. So before we talk about the building blocks for sequential logic circuit, basically the latches and the flip-flops. So most time we just use flip-flops. Okay, and today we're going to talk about how we can use the flip-flops to build some modular sequential logic. And a big type of that is registers. And this is very commonly used circuit in the computer system. Registers, and in most cases we call them shift registers, is defined as a synchronous sequential circuit that will store and move n bit of data in n flip-flops. And the movement of the data could be serial or parallel, depends on the design. Okay. For example, the graph on the right shows a 4-bit register using D flip-flops. Okay, we will talk about the operation of it later, but here you can note that unit the number of bit the register can store is the same as the number of flip-flops in that register. Because if you recall what we learned about flip-flops, one flip-flop can be used to store 1 bit of data. Okay, so that's the basic definition for register or shift register. And for short, sometimes we just call them SR. Okay, means shift register. And to name a shift register, we use SRG. Okay. And for the n-bit shift register, we just call it SRGN. All right. And depending on how the data is moved and the input and output, we have different type of shift registers. Okay. The most basic type is serial shifting, like graph A here. Okay, so which means the data, we can only input 1 bit of data at a time, and also output of 1 bit of data at the same time. That's called serials in and serials out. And we can do it in 2 different directions, like from left to right or right to left. So they are called shift right or shift left register. And we can have parallel data in but serial data out. Okay, or serial data in, parallel data out. Or we can also have like parallel in, parallel out. And the last 2 type is rotate right or rotate left. Basically, rotate means the output of your last stage is collected back to the input of your first stage. Okay, and we can also build one shift register that has all these functions. That will be called a universal shift register. Okay, so that's just about the type of that. The graph on the left here shows an example or the symbol of SRG8 or an 8-bit shift register. And this is a serial in, serial out shift register. So let's look at how this type of register works. But in order to save some time, we only do 4-bit here. Okay, the 8-bit has similar idea. Okay, the operation is very similar. So let's look at this 4-bit serial in, serial out shift register. The logic circuit will look like this. So we have one data in and the one line for data out. Okay. Basically, we collect the Q output of the previous flip-flop to the input of the next stage, the next flip-flop. Very simple. And also, we collect all the clock input together. So this is the total clock. And also, we have a reset signal here. that allow us to reset them all together. And we can tell the reset is active high here. All right. So let's look at the timing diagram of this circuit using what we have learned about D flip-flops, right? Suppose at a certain moment I have a data 1 to be input to this shift register. Like at this moment, change to 1, and this data lasts for 1 clock cycle, and it go back to 0. Okay, let's see how this data being moved in this SR. Okay, so first check Q0. Q0 is the output of the first stage, U1. Okay, and if you remember the operation of D flip-flops, also let's assume everything is reset. Okay, at the beginning, because we have a synchronous reset input here. Okay, everything is reset. So at the second rising edge here, because the D is 0 right before this edge, so Q0 will follow D, right? So it still be 0 until the next rising edge. Then at the rising edge 3, we got 1 here, so Q will also change to 1 and keep that value until next rising edge. And at here, D is 0, so it will turn back to 0 and keep 0 there. Now at the next edge, D is 0, and for the rest of the time, D is 0, so Q will follow D. So it will always be 0, right? Now, we notice that the waveform for Q0 is the D is collected to the D input of the second stage, and we know Q1 will follow D input here, and this D input is equal to Q0. So we know that Q1 will follow Q0, right? But it will lag by 1 clock cycle, because this is, you can think this is D1. Okay, so this is 1, 2, 3 here, or you can use D2, whatever. So I use D1 here. So D1, Q1 will follow D1, so it will be like this. Similarly, you will find Q2, because Q1 basically connects to D2, so Q2 will follow D2. Oh, sorry, did too much here. This will change here from here. Finally, because Q2 is connected to D3, so Q3 will follow D3, will be look like this. So now you can see that the input data can be shifted to Q0, to Q1, and Q2, and Q3 by sequence. And also we can tell that when 1 clock rising edge comes, it shifts by 1 bit, right? So it totally it shift 1, 2, 3, 4, 1, 2, 3, 4, shifting 4 bits to the output. Okay, so that's the basic idea of a shift register. Now we understand how the shift register works. Let's try a more comprehensive data set here. Okay, say we want to pass a series of data 1, 0, 1, 0. Okay, let's start from the LSB. See how will this data being passed through this register. Okay, so first the LSB 0 will appear in the data line, right? And if we start from time 0, 0 here means no clock rising edge coming. Okay, no edge, then every output of the flip-flops will stay its original value. Here we just assuming they have the reset value. So initially everything is 0. Okay, then one clock rising edge comes, which means this bit, the data here will first move to Q0. But since the data is 0, so we still have everything be 0 because only Q0 changed. Oh, Q1, Q2, Q3, no change because the input 0. And basically Q0 is not changed. I shouldn't say it's changed. Basically this is the data is not the reset value anymore. Okay, after this bit is moved here, the next bit 1 will get ready in the data line. So when the second rising edge comes, the LSB0 will be shifted to the output of next flip-flop, right? So this 0 will move to here, okay? While the second bit will shift to Q0. So you get 1 here. And for this still 0. Okay. Then after this is moved, this third bit is get ready here. So move here. And when the third rising edge comes, this will move to here. Okay, and this one, of course, will also shift. And the third bit of data will shows here. And this one is 0. Finally, the last bit of data you see, and the third clock cycle. That's how it look like, right? Lastly, the fourth bit of the data is showing on the data line, and waiting for the clock rising edge. When the fourth rising edge comes, so this 0 shift here, 1 shift here, this 0 shift here. Finally, the last bit of data will be sent here, 1. So now at the fourth clock rising edge, we stored this 4 bit of data to the 4 DFF. Okay, so this, you can think this is the store stage. How? So for the 4 bit, we need a 4 clock cycle to store the data. Okay, 4 bit of data. Okay, so if we follow the previous slide, let's continue to read the data out after we store it. If you remember, we spent at the fourth clock rising edge, we stored the 4-bit data to the 4 flip-flops, right? Now I want to read the data out. Since I can only read 1 bit at a time, so I still need like another 4 clock cycles. Okay, so at the 5th rising edge, the first bit will be read out. Like this 0 will be read out, okay, to the data bus or data line, okay, and the Q2 value will shift, Q1 will shift, this will shift too, and because there's no new data coming, so no new data means it's always 0 now, so which means the data is still shifted here, but it's always 0. Okay, now at the next cycle, this bit will be out, and this will shift to Q3, this to Q2, this 0 to Q1, and no data, so just 0 be stored to Q0. And the next cycle, this will be out, this will shift to here, this will be here, here, here. Finally, this will out, and we have 0, 0. So this now we need 8 5 to 8. So another 4 cycle to read the data out. Okay, now you see the relation. If we have an n-bit shift register, basically we need n clock cycle to load the data in or store the data. Okay, store the n-bit data. Then we need another n clock cycles to read the n-bit of data out. So 2 n's for the whole store and the read cycle. If we collect the output of each flip-flop out, okay, then we have a parallel out shift register. So in this case, we have a serial data in, parallel data out, which means when reading the data out, for example, if we store the 1010 here, this time we can directly read the data out. So we don't cast an extra cycle to read the data, but usually we have some output flip-flops here. So usually it takes one cycle, one clock cycle, or clock rising edge or falling edge. In this case, rising edge. Okay, one edge to read all the data out. So in this case, we need 4 clock cycle to store the data, because it's still serial in, but we only need 1 clock cycle to read the data. So absolutely it's faster, right? This graph shows a parallel in, serial out shift register. So basically we have two functions here. We need to load, first we need to be able to load the data in parallel, right? So which means only cost 1 clock cycle to load the data. So this time 1 clock for store the data, and we need 4 clock to read the data out. Okay, and we also need to separate the shift and the load function, so the data won't messed up. Okay, and from this input you can tell if we input a 0 here, it should load. Let's see how this works. So if this line load, actually shift, if this line equal to 0, it should perform load function, but let's see how it works. So if this line is 0, which means we have 1, we have logic 1 to gate G1, G2, G3, and G4, right? If we recall the property for the AND gate, if one input is 1, then the output of Y1 basically will totally depend on D0, right? So Y2 will be D1, Y3 D2, Y4 D4, 1, 2, 3 D3. Sorry, for D3. Okay. And also the other, since this line is 1, the other line is 0. Right, so one input for G5, 6, 7 is 0, which means the output for 5, 6, 7. So Y5 should equal to Y6 equal to Y7 equal to 0. Okay, so for the OR gate 1, 2, 3, one input is 0. So we can figure out that Z0 equal to Y1, Z1 equal to Y2, Z2 equal to Y3, and Z3 equal to Y4. So now we can tell that at this value, the input of the flip-flop actually equal to the data, the 4-bit data. Right, so once I give a rising edge here, we'll quickly store the data. So Q0 will equal to D0, Q1 equal to D1, Q2 equal to D2, and Q3 equal to D3. So we can store the 4 bits of data at the same time. Okay, now in order to read out the data, we need shift the data. So this time we need to change this shift load input equal to 1. Let's check what will happen. If this equal to 1, then we have 0 here. I should wipe this. 0 to this location. So basically, then y1 equal to y2 equal to y3 equal to y4 equal to 0 this time. Okay, then this will be 1, this will be 1, and this will be 1. Then we know that y5 should equal to q0, y6 should equal to q1, and y7 should equal to q2. Right? And then we have z1 equal to q0, z2 equal to q1, and z3 equal to q2. So if we have this collection, you will find this circuit become the same as this 0 in, 0 out shift register. So then we know how the data will be shifted, right? So this is how the parallel in, 0 out shift register works. Again, if we have the parallel in, 0 out shift register, just change the output to parallel out. Then we have a parallel in, parallel out shift register. Okay, so we have, you see we have the shift and load function here, and we have the clear, and then we have the set and the reset input for this one. Okay, and this is an example for the bidirectional shift register. So this is a 0 in, parallel out shift register, but it allowed to shift to right and left depending on this input here. So the analysis is similar to the parallel in, 0 out SR. So here we skip that, just put the basic function here. So if the right left input equal to 0, what will happen? You can, from the name you can tell it will shift left. Okay, shift left means, this means the Q2 equal to Q3, Q1 equal, let me put it another way. When it's shifting, the data on Q3 will shift to Q2, and the Q2 will shift to Q1, Q1 shift to Q0. Okay, that means shift left from larger number to smaller number. If the right and the left bar equal to 1, it will shift right. Shift to right, which means the data stored on Q0 will shift to Q1, and the data on Q1 shifted to Q2, and from Q2 to Q3. Okay, so that's the basic operation. Once we know that, we can try to generate the timing diagram for this one. So, and the control input is shown here. Okay, and let's still assume the same data. Okay, 1010. Say we initially stored 1010 at the output. Let's see what's going on. So Q0, Q1, Q2, Q3. Okay, so first we know it's shifting right. Right means this direction. Okay, so at the first edge, what will happen? So initially we got 1 0 1 0, right? First shift to right. So the data for Q0 at this edge will shift to Q1. Q0 is 1, so Q1 will become 1. Or let's put a value, maybe easier. So we got 1 0 1 0 at the beginning. So it will shift right. So I got this shift here, this shift here, this shift here. Then what happened to Q3? It's actually this data is reading out, so it's no longer there. So I got this. Then at the second edge, it still shift right. So we will shift again, and this will shift out, so no longer be stored in here. But what happens those? So here, and this will be 0 actually. Basically, it's because after the data, the real data is stored, we just reset the data input to be 0. So all the new data will be 0. So that's why we got 0 at those locations. Now at the next edge, it's shift left, right? Shift left, which means go up. So this 0 will be here. This won't be here. This 0 will be here. So this 0 will be out. This is stored in Q0, but it shift out. And the data in now is loaded to Q3. So we got 0 here. All right. Then shift left again. So we have 0, 0, 1. We have 0 here. Then shift left again. We will have 0, 0, 0, 0. Okay. Actually, we don't have to do the rest because it's all 0. All the data be the cat randomly read out. Okay. So if we draw the waveform, it should look like that. So use a different color. So the waveform for this bit, for each output, will look like this. Okay, so that's how the bidirectional SR works. Finally, let's talk about how to design shifter register. Because shifter register is one type of synchronous circuit, so we will talk about the systematic way for the design later on. So here we just talk about the ways can be used to design the SR. Okay, here is kind of shortcut for SR. Let's check the question. Say if we want to design a 4-bit SRG with control input, shift and node. Feel familiar, right? We saw this before. So, and this is how it works. If both SH and L are 0, the stored data in the SRG will not change. If L is 1, doesn't matter what happened to SH, the SRG will do parallel loading from data input I3 to I0. If SH is 1 and L is 0, the SRG should shift to the right. Feel familiar, right? We have this. So we have a control input that control the function of this register, either do loading or shifting, right? So let's again, for the design, we need to translate this into a table. You can call this state table or truth table or whatever. But because when we design sequential logic, there are many inputs. So sometimes we don't have to list everything out. We can use variables to represent those states. For example, we have two inputs here, right? We shift input and then load input. Okay, if they are both 0, we know the data will not change at all. So which means, so here I use the star representing the next state. So the next state will equal to current state, right? No change. So it's just Q3, Q2, Q1, Q0, whatever value they have, we just keep them there, right? And if L equal to 1, then we call this load. So basically the load is kind of active high here, right? So when it's active, we will do loading. Loading means the output will be changed to equal to the data input, since we are doing parallel loading. So it happens at the same time. So now Q3 should equal to I3, Q2 equal to I2, and I1 and I0 like this. Finally, if SH is 1 and L is 0, which means the SRG should shift to the right. Still remember, shift to the right means from smaller value to larger, right? So which means Q3, the next state of Q3 should equal to Q2, Q2 equal to Q1, Q1 equal to Q0, and the Q0, since when we're shifting, we don't want to load any new data, so it's just 0. Okay, then the next step is again translate this table into a Boolean expression. But you should know what is the output here. Basically, that's the so the output actually is not the output of flip-flop, because we are using D flip-flops here. So the output here actually is, we are talking about D2, D3, D2, D1, D0, because they are equal. So that's why I put it. So the real design is on the input of the flip-flop here. So that's a very different thing compared to the combinational logic design. Okay, for sequential, we are designing the input, not output. Okay, so let's see how to write the equation. So here, what we can do is that to write the equation for D3, we just knock this column. So we can translate this by using the statement. Say, so when will D3 equal to Q3? When L equal to 0 and SH also equal to 0, right? Under this condition, D3 should equal to Q3, right? Then if L equal to 1, since SH is don't care, so we don't, so which means we don't need to use it. So L equal to 1, then D3 should equal to I3. Finally, if L is 0, SH is 1, then we get Q2. Similarly, we can write D2 equal to L prime, SH prime, Q2, or L, I2, or L prime, SH, Q1. D1 equal to Q, L prime, SH prime, Q1, or Li1, or Q0. Finally, D0 should equal to L prime, SH prime, Q0, or L and I0. And the last one is 0. So it only has 2 terms for D2. So once we have this, we can do the logic diagramming. Finally, since we have the Boolean expression for the D3 to D0, we just draw the logic diagram out. So in this shift register, we have 4 D flip-flops. Okay, So like I said, we design for the input so using the two control input and the data input to forming a input circuit to send the value to the input of each flip-flop. Okay, and one thing I forgot here is we need collect all the clock signal together. So we only have one global clock signal to control all the 4 D flip-flops. Okay, so that's all for the shift registers. It's a simple circuit, but it's very useful, and you can see this type of circuit in almost all the digital systems whenever we need to temporarily store some data. Okay, like in CPU, in some MCU, always shift register. Okay, that's all. I'll see you next time. Thanks for watching.